to talk about pathogen molecular epidemiology and why it is actually, not so much why it's important to do it, which is kind of speaking to the converted, but why it's important for African scientists to do it. So when I was a PhD student, I first came across a book called Curing Their Ills by Megan Vaughan. And one of the points Megan made in the book actually struck me. It was the fact that there had been all these advances in biomedical science, but they had done very little to help the people who are delivering healthcare in Africa. And at the time, I was very worried by this because I'm a basic scientist without apologies. And I always believed that what I discovered would be taken by people who did translational work and then be used to impact lives. And what Megan was suggesting is that not that this doesn't happen, it happens, but it doesn't happen in Africa. So most of my work has been sort of focused on very, very basic molecular microbiology, trying to tease apart pathogens, trying to tell which is which, trying to tell identical pathogens from each other, almost identical pathogens from each other. And I'll admit that in many cases this is not essential. For example, if you want to implement sanitation and water interventions for diarrheal disease, it doesn't matter what's causing the diarrheal disease, you're going to get impact. Okay? If you use nutritional interventions, you prevent a whole range of diseases in young children. Okay? If a child has diarrhea, if you give oral rehydration, normally you don't need any antimicrobial in order to resolve that infection. But there are key places where you do need to know the etiologic agent. And it turns out that many of those places are the instances in which there are technological innovations. So for example, if you have a disease, this is not so much an innovation, this is a long-standing problem. If you have a disease syndrome that has many etiologic roots, such as fever. Fever is one place where we've made less progress than some other areas because there's so many different organisms that cause fever. Narrow-spectrum antimicrobials. Before you can use them, you need to know what's causing the disease. This was not an issue 30 years ago. We all used broad-spectrum antimicrobials. Now with resistance, we're realizing that narrow-spectrum antimicrobials are the way to go for certain infections. Vaccine development. If you want to develop vaccines, you need to not only know what organism is causing your infections, but also what subtype and what antigens that subtype is presenting. And then if you want to use targeted anti-vector interventions, you need to know specifically which pathogen, which vector is involved in the disease that you care about. And then you can also discover drugs that will be specifically active against a particular pathogen or subpathogen and not active against closely related pathogens. None of these concerns were very important, apart from perhaps the fever example 100 years ago. But now that we have a lot of technological innovations in the pipeline, it becomes very, very important to know what is causing each syndrome. Some of the innovations that I'm referring to, for example, is that in addition, in the objective of addressing a particular infection, we can decide to block a specific virulence factor in a pathogen, such as a regulator in this instance. If we can block the regulator that causes the transcription of virulence genes, what that means is that you have a pathogen that cannot do any harm, and then the immune system can clear it. Okay, now this was something that was sort of thought of as esoteric a while ago, but now that we have selective pressure from antimicrobials, we recognize that this kind of therapy is not going to be prone to antimicrobial resistance. And there's an example that is in I think phase 1 now, Verstatin, which is an anti-cholera drug, which inhibits the regulators that express cholera toxin, and then that way it can block dangerous disease in cholera. It's useless in other diarrheas. And so you really want to be able to have good diagnostic support for use of such a tool. In another example, you could block a pathogen binding to its site, and then that way you have an instance where the pathogen cannot have a hold in the host, and then the disease is resolved by the patient's immune system. So why should African scientists care about etiology? I wanted to bring a more recent example, an example that is actually relevant to a product that is available. And the example I picked is actually a vaccine. And what you can see here is all the stages that one would normally go through if one is doing vaccine development. And when I told people, I work at the University of Ibadan in Nigeria, they always want to say, I have this phase 1, phase 2 trial, would you like to be part of it, and so on. And I say, well, I'm actually a basic scientist, so I'm probably not your person. But you rarely get people saying, I'm really interested in the molecular pathogenesis, I'm constructing a vaccine candidate, would you want to be part of it? I think we often get invited to do things that are very low on the list here, not low in terms of importance, but low in terms of sequence. And what I would like to encourage people to do is to do some of these things above these translational stages as well. So here is a table taken from a recent publication on, apologies for the overlap at the bottom, recent publication looking at which vaccine would have, which pneumococcal vaccine would have the most impact in Nigeria. Nigeria is where I'm from, so obviously I was reading this even though I don't work with pneumococci. And there are several vaccines on the market. There's a vaccine that covers 7 different serovars. There's a vaccine that covers 10 different serovars. There's a vaccine that covers 13 different serovars now. It's getting broader. The PCV7 vaccine was developed ages ago. I have no idea why Nigeria has not deployed it yet. Many countries like the Gambia deployed these vaccines early. They've seen an enormous effect. But what you'll see in bold is the serovars that are present in Nigeria that are covered by this vaccine, okay? And as you can imagine, the more serovars you have in a vaccine, the more expensive it gets. So it's cheaper to use PCV7. But when you consider the fact that there are many serovars in bold here in PCV13 that are not covered by PCV7, it makes sense for Nigeria to use a more expensive vaccine. And be aware that there are some serovars that are not covered by any of these vaccines, which means the ideal vaccine for Nigeria has not been put together. Now imagine what would have happened if we had this epidemiological information when PCV7 was being developed. We would have liked a PCV7 that didn't have 4 and didn't have 14, which we don't really see in Nigeria, and had some of these other serotypes. It would be much cheaper for us to use, be much more relevant for our situation. We continually need this data, even with whichever vaccine we deploy, because vaccines, pathogens respond to vaccines, and the epidemiology would change as the vaccine is being used. So we've actually lost out by not having this information early. And so I'd like to encourage people to do the sorts of things that will provide this information before the tool is even available. Okay, I'm going to use the rest of the talk to just talk a little bit about what we do in our lab. And we actually study diarrheal disease. And diarrheal disease is, in a sense, one of the public health successes, in that in young children, which is what concerns us, diarrheal disease is coming down. The number of children who die of diarrhea is coming down. But the number of episodes that a child will have during their lifetime is going up because these children are surviving, and the root causes of the diarrhea have not been removed. So this is a call really for a technological intervention that will prevent diarrhea in the exposed, such as a vaccine. So there are many other technical innovations, again, that could be used in diarrhea. All of them, except perhaps some of the probiotics, require some etiologic information. Now, where do we get the etiologic information for the development of vaccines to be deployed in Africa? Many of them are in development right now. Some of them come from data that is obtained from travelers' diarrhea. Visitors from affluent countries that visit African countries go back with diarrhea, and then somebody checks what they have. This is actually the tip of the iceberg or the top of the hippopotamus, depending on the way you think. There's a lot going on down here that we don't understand. A lot of pathogens are involved in childhood diarrhea that don't actually cause a problem in travelers. The other place where most of this information comes from is large multi-country studies such as GEMS and Mallard, which are on now, that pick 4 or 5 sites in developed countries and then study what is the etiology of diarrhea in those countries. These studies are very valuable. We use them to calculate sample sizes for our own studies. But one of the things these studies are finding is that etiology varies from place to place. So we need a lot more density of this type of study. Let's skip over that in the interest of time. We study diarrhea causing E. coli, and just for those who don't work in this field, which is most people, there are so many different categories. There are 5 that have been unequivocally shown to be causes of diarrhea, and there are several other categories that are still under investigation. And within each of these categories, there are different subtypes. They all have different mechanisms of action. And some of them, not all of them, are actually neglected pathogens. The pathogen that we focus on most of all, enteroaggregative E. coli, is one that I'd almost imagine most people in the room have never heard of. It's a predominant cause of persistent and acute diarrhea among children in developing countries, including in Nigeria. And if you look at the neglected pathogens and what we're spending, very little research is occurring worldwide on enteroaggregative E. coli in basic research, drugs, and just very little vaccine development work. So I became interested in this pathogen when I was doing my thesis work almost 2 decades ago, when I found that some of the well-known pathogens, once again, apologies for the formatting of the slide, but these are well-known pathogens which were not very common. Very few of them were associated with diarrhea. And what we found was that for enteroaggregative E. coli, which is this, we had a large number of children carrying enteroaggregative E. coli with no disease and a significant association with disease. And this is a pattern that has been replicated in other countries. And what it seems to show is that this is a diverse group, some of which are not pathogens and some of which are. The pathogen is actually described by phenotype. The bacteria adhere to eukaryotic cells in a characteristic pattern. And if you're not very biased, like people who are in the field, you say, well, this is a phenotype that could be caused by anything that produces adhesins that allow it to bind to a eukaryotic cell and bind to each other. And that is indeed the case. So what we have in this group called enteroaggregative E. coli is actually a mixed pot. And so we decided to resolve it using genetic methods. And so what we did was, in the days when sequencing was very expensive, was to sequence 7 genes in a multi-locus sequence typing protocol for all the strains that were obtained in this study, and then try and subclassify them. And to our surprise, there was an incredible amount of diversity. So what you're seeing here, every dot represents one lineage of E. coli. Most E. coli are commensal, so most E. coli don't cause disease. And the dots that are surrounded with pink are those that are enteroaggregative E. coli. So not every E. coli is an enteroaggregative E. coli, but there are several lineages, and I just circled the major ones to show you sort of the level of diversity that we're talking about. We then broadened this study to include isolates from other places. So we have isolates from Bangladesh, isolates from the UK. And all I want to show you at this point is that now that we have major clusters emerging, that we know that those who are targeting vaccine development should focus on, some of these major groups include the Nigeria strains, which naturally are in green, whereas others do not. And that means that if we had not sort of laid the foundation with the Nigeria strains, you have a situation where those who are working in vaccine development now would be developing vaccines that would be completely useless in our context, even though it is from Nigeria that we first learned that this is an important diarrheal pathogen. So I do want to encourage those of you who are working with pathogens that when it comes to things like molecular biology, subtyping, and so on, when you're told, oh, this can be done in France, it can be done in Belgium, it can be done in the United States, why not suggest that, well, it needs to be done here with my isolates? I gave examples from childhood infection, which is sort of what I work on, but this is relevant in almost every infectious disease, particularly some of the infectious diseases that people in this room work with. So I'd like to encourage you to do that. I'd like to just end here, thank those that work with me now, my collaborators elsewhere, and our sources of funding. And I really want to thank the organizers for inviting me as well.